did.
You're Arkansas.
Yeah, I've been in Arkansas for a while. Yeah, so I went to just finished graduate school at UAMS in Little Rock. So
Okay,
just bouncing around
good.
Arkansas.
So you're you're in Arkansas.
Yes, yeah. For the past, I guess it's almost been 10 years when it gets to August. So what the fuck?
That's great.
Put it all together.
That's great.
Yeah, I like it so far. You know, it's a little cool, a teeny bit cool. You know, we at least get more snow, which I think is fun. But, I enjoyed last week, but had to shovel a lot of stuff.
Yeah, so you wouldn't have it all the time.
Right. That's or at least if it was there and it was the nice fluffy stuff for longer, that would be
But
good.
not the ice.
Yeah, no, that's
They are always like slipping out, kind of like fastest in the ground. I'm Wesley, by the way.
Well, I'm glad you're here.
Yes, thank you. Yeah. Thank you for the welcome. And yeah, Arosha and Monfan have been super welcoming as well. And Dr. Crafton as well.
Good.
Right, we have technically he's a chemist. It's kind of nice to have another extra
Of course.
chemist on board.
Absolutely, I'm sure.
And yeah, thank you for being very supportive to the department. She has bought like glassware sometimes.
Oh, wow.
Yeah, I'm
Yeah,
so
we're
glad
never
to
short
see
on
you in
glassware.
person. I don't think we have met.
You
in
know, we
person.
may not have actually met. I've obviously heard so much about you.
No.
Good things
Right.
that
Right. And that's great. Okay. Oh, you can make it.
Beautiful Thursday outside. We're all happy to see that the ice is melting, and it's a good way to spend the afternoon to hear from Dr. Perera, who hopefully many of you have had a chance to meet during her time here. She's a Fulbright scholar, currently studying at Minnesota State University. She did her PhD at Oregon State University. She's a professor of chemistry at Colombo University in Sri Lanka. She has a longtime friendship with our own Dr. Irosha, and her husband, I understand it, is a good friend of Dr. Vijatunga. So she has connections here on campus, but it's an extraordinary honor for us to have a Fulbright scholar here on campus this week visiting with us to share her experience, both being a student who went across the world to earn her PhD, but as a researcher, and today we get to hear more about her research, and I'm particularly looking forward to that. So Dr. Perera, please take it away.
Okay, so thank you very much for that introduction. So good evening, everyone. So that's the topic that I'm going to talk to you today about. But before doing that, for the ones who have not been into one of my talks, I'll tell a little bit about my country. I've been doing that for the ones who has missed that. So let me tell you a little bit about Sri Lanka. So it's a South Asian country that's located close to India, in the Indian Ocean. And something that is famous in Sri Lanka is Sri Lankan tea. So if you're a tea lover, you might think, okay, I haven't heard of Sri Lankan tea, but I'm sure you've heard of Ceylon tea. So Ceylon tea is one of the very good teas that's available in the world, and that's Ceylon name came because we were under English and they called Ceylon. So after the independence, it became Sri Lanka. So it's from the central highlands of the country that we have these tea plantations, and the Ceylon tea is originated. And also it's an island, so we have beautiful beaches and nice sea life. If you're interested in snorkeling, would be the best place to go. You'll see sea turtles, you have reef sharks, so many beautiful fish. And you have a unique way of fishing. You can see it in the picture there, where people balance themselves on a stick and fish in the coral reef. Actually, Dr. Vijayatunga reminded me that it's his hometown that they fish in that manner. So when I said that, he said that's his hometown. So that's that. And also, it's a country that is having one of the virgin forests that's remaining there in the world today, which is the home to many endemic animals in Sri Lanka. So all these animals are endemic to Sri Lanka, not just them. There are so many plants, other species as well, and we are having so many other. If you like to go safari, that would be the best country to go. You would see herds of elephants, leopards, you'll have monkeys everywhere. So it's a nice place. And also, it's a country that's having a very rich heritage. So this rock is called Sigiriya, also known as Lion Rock, and it's a UNESCO heritage site, and it's built in the 5th century. And the architecture there today, and the engineers are still amazed how it was done in those days. So that's a little bit about the country. And so this is the university that where I obtained my bachelor's degree, University of Colombo, as well as Irosha and Dr. Taranga. So that's the same place that I'm working today in the Department of Chemistry. And all the work that I'm presenting is carried out at the University of Colombo. And this is the oldest university in the country. We celebrated 100 years in 2021. So that's a little bit about the country and the university that I work in. So now let me just move on to the research. So the topic that was given was electroanalytical chemistry in action, applications across health, environment, and technology. So I'm going to start off with health. So it's one of the sensors that we developed. It's a non-enzymatic electrochemical sensor to which we have the UK patent for. So if I tell you a little bit about the background of this sensor, it's a sensor that is capable of detecting the menstruation cycle of the human. I'm sure now you might wonder, like, there are so many commercially available strips to detect this. So why do you need one? So yes, I agree, it is available. The most commonly available one is this urinary LH detection using the enzyme immunoassay, right? But there are some disadvantages of this immunoassay kit that's available, mainly because it's based on enzymes. It is not very stable and it's very expensive. So, and also you cannot reuse it. It's only a one-time use. So our idea was to develop a sensor that can detect the ovulation of the female and the menstruation, as well as it's reusable. So for this, we have used this compound. We call it CTAB. It's cetyl trimethylammonium bromide. So a little bit about the chemistry of the compound. You can see it has a long carbon chain. So we are mixing it with graphite. Again, non-polar substance. So these two non-polar substances mix very well. And the positively charged N group will sit at the corner. So graphite will have a positive charge when it's mixed with CTAB in there. And the enzymes in the menstruation cycle, especially we were specifically looking at estrogen enzymes. So they, in the anionic state, they can attract to each other. So the positives and the negatives attract, so they can get absorbed. So that's how the selectivity is obtained in the sensor that we developed. So this is the electrochemical setup that we have. So working electrode is consisting of 5 millimolar CTAB that is modified with that is mixed with graphite, and it contains the paste nature is coming from polyurethane. And the counter electrode that we use is the unmodified graphite, so it does not have CTAB, unmodified graphite in varnish paste. And the reference electrode, we are using a pseudo reference electrode, which is a silver ink. So this is how the setup looks like. So they are all pasted on a fabric base, and the top part of the fabric is made hydrophobic using the polyurethane, and the bottom part remains hydrophilic. So you have the fabric in there, and we paste and we place another fabric on top, and the sample is introduced onto this fabric for the testing purpose. So this is the setup that we have used. Now, before looking at human samples, we have characterized this sensor. And so characterization of this sensor we carried out using the two hormones that are in the menstruation cycle that regulate the menstruation cycle, the main two, estrogen and progesterone. So we have tested these two hormones on the sensor, and we have seen, so EED is for ethinyl estradiol, that's a form of estrogen. So it gives a considerably high current peak when tested alone by itself. And when you test progesterone, that's giving, there's no current at all, there's a very small peak. And then we've decided to test them both together, because in the human we are testing human urine, and you're getting estrogen as well as progesterone together in there. So we tested both at the same concentration, estrogen and progesterone together. So you can see that there is a reduction in current when progesterone is present with estrogen in there. So this is something that we see across different concentrations. So these are concentrations, the concentration we have increased by 10-fold. And you can see in all the concentrations, when we have estrogen alone, the current response is higher compared to when we have estrogen with progesterone. So this is an observation that I want you to keep in mind when we are looking at the human samples that we have tested. So before moving on to human samples, just to remind you of how these hormones work. So this is how the hormone levels change in the blood of a human over the menstruation cycle. You can see the blue line is estrogen, and estrogen, you can see there is a peak around the halfway point of the menstruation cycle, that is 28 days long. And right after the peak, you can see the ovulation. So basically what we try to do is to see whether we can detect that peak in estrogen. So then if you know that, then you know right after that you have the ovulation. And the other observation is that you can see after that you have a kind of a broad peak for estrogen, as well as there's another broad peak for progesterone. So both of estrogen and progesterone are giving broad peaks. That means basically the concentration of progesterone increases as well as the concentration of estrogen increases in the blood. And when that concentration decreases to a small value, then the menstruation is taking place. So these are the two phases that we tried to see whether we can detect using our sensor. And so this is in the blood, but we wanted to use a non-invasive method. So we used urine samples. So this is you should be looking at the pink color graph. That's the one where you have women from aged 19 to 36. So you can see even in urine, the top graph is how the estrogen hormone is varying, and the bottom one is how the progesterone hormone is varying. So you can see that exact same variation that you see in blood in urine as well. So, so this is basically what we try to see with our sensor. Okay, so this is actually 3 menstruation cycles of one female and who is having regular menstruation, and you can see that we were consistently able to detect the estrogen peak using our sensor as well as the broad peak. We are not seeing a very high intensity. We believe that's because progesterone as well as estrogen is there in the sensor, and progesterone reduces the peak intensity. Still, you can see this broad peak. So we can successfully identify the ovulation of human as well as the menstruation of humans. So this is just one sample, and we have tested several. I've just put several of them in here. Again, another female that we have tested. You can actually clearly see the peak for estrogen. So we can clearly predict the ovulation, and we have actually tested whenever we see the peak, we have tested it with the commercially available strips, and it gave the positive response on the strips as well. So it is proved that we are seeing the ovulation with the peak. And the broad peak is not very prominent, but if it's mostly it's the ovulation that we can predict than the menstruation using these sensors. So this is, this is something that you can do with the commercially available kit as well, because you can just count the dates. They're all regular cycles, so you can count the dates and figure it out. So we wanted to test whether we can actually predict the ovulation for a female who's having irregular cycles. So that's 4 cycles of a female who's having irregular menstruation, and from 4 cycles we were able to actually correctly predict ovulation in 3 cycles, where you can actually see a peak that is a considerable peak, and it was confirmed with the test kit that's commercially available. So it is quite useful in predicting ovulation. And another important fact about the sensor is its wash stability. So it is quite stable when you wash. We have used the sensor over and over, more than 100 times one sensor. So it is stable. And you test it for washing stability. We have tested this is the washed sensor response and the fresh sensor response. It's quite stable under washing conditions. So actually, this kind of like the summary of this non-invasive electrochemical sensor that we developed. So it's a non-invasive sensor because you don't really have to use needles or anything. It's just urine that we are using, and it was developed on fabric and to detect hormone variation in the human menstruation cycle, and we used CTAP as the selective compound, and we used a 3 electrode system for the detection purpose. And with the testing developed sensor with real urine samples of 4 individuals, I'm presenting only 4 individuals here. It has been confirmed that the sensor detects menstrual hormone patterns of individuals having regular menstrual cycle as well as who have irregular menstrual cycles. And it can be washed with 0.1% detergents and can be reused. So that's basically about the sensor that towards the head. So now I'm going to move on to a different factor, different part of a research that we have carried out. It's applications more towards the environment concerns. That's the development of coating to prevent corrosion, to inhibit corrosion there. So if I tell you, I'm quite sure you're now very familiar with corrosion, but corrosion creates problems of durability in many parts of the world. So preventing corrosion is quite important. Like it creates pollution and it minimizes wastage. So it's very important if we can inhibit corrosion effect. So we were interested in developing a coating that can be used to prevent corrosion. So if you talk a little bit about corrosion, in order for corrosion to take place, there are factors that are needed. So one is humidity. You have to have water in there, and you have to have oxygen in the air, and corrosion is facilitated by ions that are available, electrolytes in there. Right? So if we can prevent any one of these things or all of them, then we can prevent corrosion. And another thing is corrosion is oxidation of metal. So the metal will release an electron and become an ion. So that's basically what corrosion is. So what we have to prevent is this oxidation process. So one way of looking at corrosion or preventing corrosion is trying to make the surface hydrophobic. Right? If the water is not going to get retained on the surface, we are taking off the factor that is needed for corrosion. So if the surface is hydrophobic, then we can actually reduce the rate of corrosion by So that's basically what we had in mind. So we've prepared this nanocomposite coating and characterized them. So just, I'm not going to go through the process, but we've prepared the silicon oxide nanoparticles and PS nanoparticles, and then the silicon oxide nanoparticle was modified using this octyl triethoxysilane, and the coating was prepared in the way that is given here. And this basically is the SCM image of the coating that we observed. And the coating is having nanoparticles as well as micro-sized particles. So it's not just nano coating, so it has micro level size particles as well. So we have tested this coating, one by this weight loss data. So we've tested the uncoated iron comparison to the coated iron with our coating. And so the first method is the weight loss method. So the weight loss method, what we do is we immerse this iron sample in a solution of 3.5 weight percentage of sodium chloride for 21 days. And you take the initial weight, and then you take the final weight, and then from that you can determine the weight loss. So if you take a look at these results, you can see that we have the coated iron, the corrosion rate is 0.0028 millimeters per year, whereas for an iron, the same size iron sample, it is 0.069. So it's almost 25 times higher corrosion rate compared to the coating that we have. So the coating is actually very good in preventing corrosion. It is from the weight loss method. And we have looked at the hydrophobic nature of the coating. What you see here on this side is the iron, the iron plate that is not coated with the coating, and you can see that the water droplet is having a water contact angle of 75. So basically, I think that's something that I forgot to mention. The water contact angle tells you about hydrophilicity or hydrophobicity of the surface. So let me just really quickly go. So if the water contact angle is less than 90 degrees, that means it's wetting the surface. So the water will remain on the surface. So if it's less than 90 degrees, we call it a hydrophilic surface. And if it's more than 90 degrees, it's a hydrophobic surface, so the water will be repelled. If the contact angle is greater than 150 degrees, then it's going to be super hydrophobic surface. So the water will not retain on the surface, it will just move away. So that's basically what we wanted to see during this here. This is the uncoated iron surface. You can see the uncoated iron surface is hydrophilic. It is having a contact angle. So the left is this side angle, right is the other side angle. So the water contact angle is 75 degrees, which is less than 90 degrees. So it's a hydrophilic surface. This is with our coating on the iron surface, and you can see the water contact angle has increased to 158. So that is super hydrophobic. So when a water drop falls onto the coating, it will not retain on the surface, it will flow away. So we have made the surface hydrophilic. So with that, we are getting corrosion prevention as well. And we've tested this coating. We've immersed this coating with the iron surface with the coating in the 3.58% sodium chloride for more than 24 hours, for more than 1 day, and then tested whether it's changing the hydrophobicity when it's placed in sodium chloride. Still, even after 1 day of immersion, we see a water contact angle of more than 150 degrees. So the hydrophobicity remains in the coating. So we've tested this coating with the electrochemical testing as well. So the very first one that we've tested, we've looked at the open circuit potential. So basically the red color is the one where we have the uncoated iron specimen, and it's having a more negative potential. You have more negative potential, that means negativity comes from electrons in there. So if you have more negative potential, it has a higher possibility for electrons to go away and the surface can get oxidized. So if the potential becomes more towards the noble side, so becomes more positive, then the ability of the electrons to go away reduces. So the oxidation potential reduces. Right? So we actually see that the open circuit potential of the uncoated iron sample is more than the coated iron sample, because we are going more towards the noble potentials. So it has more resistance to oxidation, more resistance to corrosion. Also, this is the Tafel plots, basically the current density versus the potential curves. So the point where these two lines intersect gives us the corrosion current. You can see again the coated sample is having much less corrosion current. This is the log current density that you see. The coated sample is having something close to 10 to the power minus 5 amperes, whereas the uncoated sample is having a current of 10 to the power minus 4. So the uncoated sample current density is much higher, giving rise to higher corrosion rates. Same with the impedance spectra as well. Uncoated sample is having less resistance to corrosion compared to the coated sample. So all these tests show us that our coating is much more resistant to corrosion. And so just in summary, in this we have developed a new super hydrophobic coating that is composed of micro and nanoscale particles, and which has the hydrophobic nature because of a contact angle of 158 degrees. And this can be used to coat electrical equipment because it has an electrical insulation of 200 mega ohms and the thermal conductivity of 0.8 watts per Kelvin. So we can use it in those activities, and this is actually a summary of what you can see. So A is the coated iron sample and B is the iron. So we have exposed them into a salt chamber for 8 days. It's the salt is sprayed and kept in a chamber for 8 days, and you can see there is no change to the coated iron sample, whereas the iron that is exposed is corroded very much. So it is quite good at preventing corrosion in the iron in the presence of sodium chloride. That's what we have tested. So that's actually about the environment, and the last one that I'm going to talk about is how it's applied in technology. This actually is not published, it was just accepted yesterday, so I don't have the paper there. But so this work we have carried out in fabricating wash durable conductive rayon fibers. So the wash durability is important because we are thinking of using this in smart textiles. So if it's used in textile, it has to be wash durable. And smart textile is the I think the industry of today, like that's what is being researched these days. So so conductivity is quite important in smart textile in communicating between the biological fluids and the instruments. So in here we are using conductive yarn from natural fibers, and it is important that we use natural fibers because they are sustainable, biodegradable, as well as they have zero carbon dioxide footprint. So that's the idea behind this this project. We have used the cotton wool to create the rayon fiber, but the idea we are working on is to use the let's say like the cotton that is discarded or the clothes that are discarded, so we can use them and extract the rayon fiber and make them conductive. So that's basically what we are working towards. Now, if I tell you how we made the conductive fiber, so we are using cotton wool, and it's dissolved in the cuprammonium solution. So you have this blue color solution. It's once it dissolved, we have like a very viscous solution, and this viscous solution is taken onto a syringe, and it's ejected onto a spinning bath with having this concentration. And so this is the regenerated fiber that we get. So the fiber, once the color disappears, we wash it well with distilled water, dry at 55 degrees Celsius, and then pre-treated with ethanol and dried in air. And this is the fiber that we use to make it conductive. So the conductivity of these fibers are obtained using the conducting polymer P.PSS, which is polyethylene dioxythiophene, that is doped with polystyrene sulfonates. It's a conducting polymer that is highly conductive. So we are just immersing it in the conducting polymer and achieving the conductivity into the rayon fiber. So basically, this is what you do. You just dip it in the conducting polymer solution and make your fiber conductive. So these are the so this is how you this is one of the fibers that are the bare rayon fiber from the bright field microscope view, and you can see the SCM view of that one as well. And this is once it is immersed in the conducting polymer solution, and we have immersed this fiber 5 times. So you immerse it, dry it, and then immerse it again. Likewise, you do it 5 times, and you get this. And the last fiber that we have here is we have immersed this fiber in the conducting polymer solution and then treat it again with ethylene glycol. So the main reason behind these two, the first time we kept on immersing the fiber in the conducting polymer solution because the conductivity of the fiber increase. The more you immerse it in the conducting polymer, the conductivity of the fiber increases. So we kept on doing it on several types to get more conductive fiber. But the issue with that is more you immerse the fiber in the conductive polymer solution, the more brittle the fiber gets. So it's not very, you cannot use it much. But when you use this method where you immerse it just one time in the conducting polymer solution and then you post-treat it using ethylene glycol, then you get the same strength, not the brittleness, but the conductivity is conductivity of these fibers are equal to the conductivity of a fiber that has been immersed 5 times. So we decided to go ahead with the conducting polymer and ethylene glycol post-treated fiber for our experiments. You can see how the resistance changes. The resistance of the bare rayon fiber, of course, you all know, I don't think it is conductive like the normal rayon fiber. So it has a very high resistance, and compared to that, both the fibers are having very less resistance. But if you take a look at the two, you can see this is P.PSS, just one-time coated fiber. The resistance is higher compared to one-time coated and ethylene glycol treated. So once you treat it with ethylene glycol, we get the required conductivity with less, like good strength, tensile strength. So we have tested it for its tensile strength. The cross-sectional area is actually taken from the SEM images and the tensile strength using the tensile strength machine. You can see that the tensile strength of the treated fiber is few times higher than the tensile strength of the bare rayon fiber. And we've actually tested it for the wash stability. We've tested the two fibers that I talked about with the fiber that is treated 5 times with the conducting polymer and fiber that is treated 1 time with the conducting polymer and post-treated with ethylene glycol. And you can see that ethylene glycol treated fiber, the resistance increase is much less. So it is more washable compared to the P-dot only coated fiber. So the first graph is the washing using detergent in the aqueous medium, and the second one is for dry cleaning solvents. So in both media, we see that the fiber treated with the conducting polymer and post-treated with ethylene glycol is more stable compared to the P.PSS fiber. So we've decided to work with the ethylene glycol post-treated fiber. And so we've tested them. We can use them as electrodes. So we have taken the fiber. So this is actually several fibers woven together, and we've connected it to a copper plate, otherwise we cannot clip the alligator clip there. So, and we have tested them in solution to see whether the conductivity changes. The resistance, you can see there is a linear response when the concentration of sodium chloride increases. You can see the resistance decreases, and we are obtaining a linear response using these fibers that we have. The conductance also we have tested, and you have not, the linearity is not as great as the resistance, but still it's quite good linear response with conductance as well. We have tested them as electrodes, whether they can be used as electrodes. So we've done so this is using the rayon fiber that is connected. We've run cyclic voltammetry at different scan rates, and we've done the Randall-Sevitz plot for cyclic voltammetry, and you can see that we get the linear response for the anodic peak current as well as the cathodic peak current, telling us that these can be used as electrodes in any system. And we've looked at the impedance spectra of these fibers as well. We can see that there is impedance spectra giving us two semicircles, which is about the resistance of the electrode and maybe the charge transfer resistance here. And this part is talking about the diffusion of ions onto the electrode surface. So basically, it is a typical graph that is expected from an electrode, telling us that it can be used as an electrode. So that's actually what we saw with these fiber electrodes. So in summary, we've developed a sustainable approach in developing low-cost, flexible, and most durable fiber-conducting polymer composites with potential applications in as organic electrode material. And conducting properties were imparted using the polyethylene dioxythiophene and polystyrene, that's a conducting polymer, and post-treatment using ethylene glycol. And the modified fibers also exhibited very good mechanical properties, including high breaking load and good tensile strength. So all the other experiments that we carried out tell us that it can be used in as an electrode material in the future. So that's actually basically what I plan to present. And so we'll end my presentation here, and I'd like to thank, there are so many people that I would like to thank, so I'm just going to leave it here. Thank you very much. Thank you very much for being here.
So in your second section, when you were talking about how you were creating a coating for a metal to prevent corrosion, you tested that metal and the coating in extremely hot temperatures, but you also didn't test it in colder temperatures when there's more dissolved oxygen. And if oxygen was the reasoning for the corrosion, why didn't you also test it in those cold temperatures?
Oh, we actually did the usual room temperature ones. Usually, I think that's a good suggestion. Next time, I think we should go for all temperatures, but we did only the room temperature testing. However, the rates are usually high at higher temperatures compared to lower temperatures because the kinetics gets slower at low temperatures compared to high temperatures in general, I'm saying. But yes, that's a good suggestion. That's something that we should.
I didn't know that. Thank you.
Yeah.
In your last section, you were talking about the fibers that were coated in the substance that made them conductive and thermally conductive. What's the lifespan on a material like that if used in an application?
That is something that we haven't checked. The problem will be with actually the tensile strength, I believe, not the conductivity, because the conductivity usually stays for a long period of time. We have tested it for like a month. It's still working okay after a month, but then we have not continued. So that is something that we should actually look at some. But the issue would be, I'm thinking with the brittleness of the fiber. But then what we plan to do, because it's a very small fiber that is there, we cannot use the fiber as it is. So it's the yarn that we should test. So then the brittleness of the fiber will not be an issue when we connect it into a yarn. So we have tested for like a month. So for a 1 month, they're okay. We are not. We have not gone further than that. No, sorry.
On the metal corrosion study, you showed a small table that extrapolated the thickness of the metal that would be lost in a year for the coated versus the uncoated.
Yes.
How did you I mean, you measured it after 21 days in the salt solution.
Oh, it's
So
yeah.
could you talk about how you measured that thickness loss? And over how many samples was that average that you gave us?
Oh, that's actually from 5 samples. You take 5 the size, the same size samples, 5 coated and uncoated. So it's the weight difference that you take. You take the initial weight and the final weight, and then the millimeter per year thickness is based on the calculation. You take the density,
Surface
and
area?
yes, surface area, and that's the calculation that gives you. That's why it says the weight loss method. Also, we are just what we measure is the initial weight and the final weight. And
How do you know if that weight loss then was the surface coating coming off or metal loss?
I don't think you can really say that. It could be the surface coating coming off as well. We can't really say it's for the ones that are uncoated. Definitely, it's the metal that is coming off. But for the coated ones, you can't really say which one gives rise to the reduction in weight, whether it's the coating coming off or whether it's the metal loss. But the experiment, the way that it's carried out is from the initial weight, and then you look at the final weight. So it's the weight loss method. That's how it is done. You can't clearly say that weight loss is due to metal in there. Could be the coating as well.
I'll steal an extra question about the ovulation detector. Could you put that slide back up that showed the 4 irregular cycles?
Yeah. This.
That one. So, a lead-in question first. How consistent are your sensors in response? Like if you measure the same sample with 10 different versions of that sensor, how consistent is the response?
It is very consistent. It depends on the size because we are measuring the current. So the current is dependent on the size of the electrode. So if you maintain the electrode size constant, then the result is constant. So what we have is the average of three sensors that are taken, and the standard deviation is quite small. Actually have,
So the reason I wanted to ask that is to lead into the next question, because looking at the y-axis scales there, on the one in the upper left, the scale is much larger.
larger than the others, yeah.
And so what really doesn't count as a peak at all there, like at 0.2, where it's about 50 microamps,
I get it, yeah.
is the peak in the other one.
Yeah.
So if you are a patient that's using one of these, how do you know that when you get to 0.5 in the first one, or point number 5 in the first one, and you get a response of 50 microamps, how do you know that's not ovulation? It seems like you only know that after you see the whole thing, and by then it's too late.
You actually have to see the one thing is you have to actually see the like one cycle you would have to see. At least we have not been able to create like an algorithm where you can look at the baseline, and that's something that we tried, whether we could do the baseline, and if it's some 3n plus 3n is the peak. We couldn't something that we couldn't.
That's exactly, you hit exactly on what I was getting at, because in the case of this patient who has an irregular cycle, it seems like it's almost impossible to tell at any given time when ovulation occurs until the whole cycle is complete, because it varies so much between.
Actually, no, because when you see the increase in peak, increase in current, comparatively, now we are comparing it with respect to 24 to 25. So when you're doing it every day, you can see the increase in current. So then we can say that it's predict. You can't say it based on the absolute current value. we have different currents because we actually had two sets of sensors. We had some manufactured, like screen printed sensors, and the ones that we made in the lab. So the sizes were different. So that's basically why you see some of them with very high current and some with low current, because of the size of the electrode was different. But I mean, like when you're looking at it, you can see like the pattern when it increases after like the baseline peak starts increasing, then you do see a high current on one day. So then you know that's after that you are seeing the ovulation.
But I guess like in 0.17 up there in the upper left, how would the patient know that 0.17 is not ovulation? Because the current increased to, what is that, about 90 microamps?
Oh, this one.
The
very last one?
upper left,
This one at
No.
the top.
other side.
Oh, you mean the?
Yeah.
Oh, I.
So when they get to the point number 17, okay, the currents increase, it must be ovulation, but it's not. And they wouldn't know that until they got
Until
to
they get-
day 25
I
there,
agree.
or 0.25.
Yes.
That is.
I agree.
So it's interesting work. I like it.
Yeah, we actually try to see whether we can come up with like, okay, this is our baseline, and beyond that, if it's more than 3 times or more than 4 times, but that-
Much easier with
that
the regular
doesn't-
cycle. than-
Yeah, so I think we will have to keep on working on the algorithm before moving on. But yes, I agree. Yes.
I have 2 questions. One is on this. So you talked about how progesterone kind of like mess up the estrogen peaks, right? Like, do you know why? Like, I know you started talking about estrogen being anionic and the sensor doing that. Is it because progesterone is being like, cationic or something?
I don't think so. One thing that we thought is, well, this is anyway optimized for estradiol. We used estradiol and optimized this the potential that we work using estradiol, and so having progesterone in there, so not getting a peak for progesterone was something that we were okay with, because I mean it's optimized for estradiol, so we did not expect to see a peak for progesterone, but having progesterone in there, it reduces. That was something that really we couldn't get. It's not. So it could be that progesterone is blocking the interaction of estradiol with the surface of the electrode. That's something that we thought of, but we could never prove it, or we didn't really work on that one. But that's something that we should look into as well.
And very similar one towards the very last part of it. You talked about how polyethylene glycol started enhancing like
Ethylene glycol, not- yeah.
ethylene glycol.
Mhm. That of course we know. I actually had a nice diagram of explaining that as well. So P dot PESS, polyethylene dioxythiophene and polystyrene sulfonate, they have entionic interactions. So PSS and P dot, when they are together, their entionic interactions, they actually keep them together in like closed circular. So P dot is hydrophobic. So it stays inside, and the PSS is like a cover outside. But then when you add ethylene glycol has interactions with polystyrene sulfonate. So now polystyrene sulfonate is no longer there to keep polyethylene dioxythiophene in one place. So they are in different, so you have more conductive parts when ethylene glycol is there than when you don't have it. So that's basically why ethylene glycol increases the.
That's pretty neat. Yeah, I really thought all the applications are pretty cool, seriously.
Yeah. Thank you.
Well, we are at 5 o'clock, and out of respect for everybody's time, let's give her one more round of applause. I feel sure she would be happy to entertain people coming down and asking her individual questions if you have.
We do have food set up in the rotunda, that the convocation committee is sponsoring, if you want to stay and chat with her and have some snacks.
Hasini,